Hi everyone, in this video I'm going to show the other direction of the Riemann-Lebesgue theorem. This one we're going to prove that if the measure of the set of discontinuities is 0, then our function is in fact Riemann integrable. Before we do that we have to prove a lemma, which is shown here. It's not too bad of a proof. So if I take f bounded on a closed interval and s positive, I define this set A sub s to be where the oscillation of f at the point x is greater than or equal to s. So basically, it's measuring how big of a jump you possibly could have. This set AS is compact for any s, is the conclusion. So we're going to show closed and bounded is the characterization of compact that we're going to show here. So first of all, AS is contained in a closed interval just from our construction of our domain. So AS is bounded. So all that we have to show is that its complement is open, which is equivalent to showing that the set itself is closed. So let's take a point in the complement, which to get it in the complement, all we have to do is take this inequality here and flip it. That means it's in the complement. So we have the oscillation, and I'm going to call the oscillation t so that I don't have to keep rewriting it. So by definition of oscillation, let delta positive be such that the set oscillation of f on the ball of width delta around x is a minus t is less than epsilon, where epsilon I'm going to pick as s minus t over 2, which is greater than 0 because s is strictly greater than t. That will imply that the set oscillation of f over b delta of x is less than t plus epsilon. Okay. So I want to show that b delta of x is contained in AS complement. So let y be in b delta of x. B delta of x itself is open. So let eta positive be such that b eta of y is contained in b delta of x. Well, that implies that the set oscillation of f over the possibly smaller subset, it's contained in it. Well, it's a supremum, so if I shrink the set, I shrink this supremum, and we showed that this is less than t plus epsilon. And t plus epsilon, I'm going to go over here. T plus epsilon is t plus s minus t over 2, just from definition of what we chose epsilon to be. And you just get combined denominator here. That's less than 2s over s because t is strictly less than s, and that's s. So that tells us that y is in AS complement. Y was an arbitrary element of b delta of x, and so that is contained in AS complement. So AS is indeed compact, like we wanted. So that's it for the lemma. If that's a bit fast, pause the video, rewind it if you need to review any of that. This will be one of the major lemmas we use in our major result here. So now we're ready for Riemann-Lebesgue, part 2. So same setup, f on a closed interval bounded, set of discontinuities here, remembering that a function is discontinuous at x if and only if its oscillation is strictly greater than 0. It's continuous when it's equal to 0. and we're going to assume that the measure of this set is 0. And we're going to show that f is Riemann integrable. So I think this proof is a bit trickier because what you actually have to do, so how do we prove Riemann integrability? We construct a partition, and then we show that the difference between the upper and lower Darboux sums is less than epsilon for every epsilon. So the construction of the partition is the major part here. Once we get the partition showing that the upper sum minus the lower sum is less than epsilon is ultimately easy, like it's just a few inequalities. So at the end of the day, we want one term to be on a small set, the set of discontinuities, where we can't control how big the function difference gets. And then we want sort of a smooth part of the sum. If we can get the, so then the smooth part, we have that the difference between f on that interval is small. We don't care how big the set is, but the difference is small, so that term is small. And then the other one, we don't know how big of a difference it is, but that's only a very small number. So if we get one less than epsilon over 2 and the other one less than epsilon over 2, that's less than epsilon. So that's the main idea. So we set epsilon greater than 0. I'm going to take, so f is bounded. So I'm going to take capital M to be its supremum, lowercase m to be its infimum. And I'm going to assume that capital M is strictly greater than lowercase m because otherwise it's a constant and it's trivial. So for s greater than 0, define the set that we had in the lemma. So it's the set where the oscillation is greater than or equal to s. And so the first major step, I would say, is to get an open cover of AS here in green. So how do we do that? Well, AS is contained in the set of discontinuities, and the set of discontinuities has measure 0. That means that the measure of AS is 0. So there exists a countable sequence of open intervals such that their measure, such that the union it's a cover, it's an open cover of AS such that their measure is less than epsilon. Okay, so I'm going to have a quick aside over here that I've written down to address this quickly. Again, if this is too fast, pause the video, review it if you need to. So if you take any set, any measurable set, this is the caveat. So I told you previously that an arbitrary element of an arbitrary measurable set in the sigma algebra has open intervals unioned with complements of open intervals. And you basically, I want to address this issue of, oh, hey, Tyler, what you told me that there could be complements in here, but you just said, okay, forget the complements. This is why. So if I say that these JNs are an open interval, but we have the complement, then their complement, we're in a relative topology. So this doesn't go all the way to negative infinity. And this doesn't go all the way to infinity. We're closed by A and B here. So I can rewrite this set to put an open interval here and an open interval here, and then union with a singleton. Okay? Now this set here is open in our relative topology. That is the major point here. So that's open, because we're in a relative topology, so we intersect back down. And then these singletons, I can always put some small delta n around them, and I grew the set, so that's a subset. A is contained in this new union, where I now have a union of a bunch of open intervals, but then I can just rewrite that. I just reindex. And so, but the only difference between these two sets was these guys. I added some points here, but then I took their difference to be small as a function of n, and then I can choose them small enough so that this series converges to a really small number, and that goes to 0 as epsilon goes to 0. If you want, you make epsilon, divide that by 4 if you want to make that clean. So that's basically all that's going on there. It's sort of a minor point, so I don't want to spend too much time on it. Then from here, we're going to invoke compactness of AS. That's why we wanted that theorem. So I want to switch back to orange here. So let I1 to IN be a finite subcover of A sub S. Why can I choose the first N? Well, relabel if necessary, so that I don't have to do N sub J. Then we note that for X in AB minus this union, such that the set oscillation, or not, yes, so the oscillation is so the oscillation of F at X is less than S. So there's delta sub X greater than 0 such that the set oscillation of F around this ball is less than S. Now, the union this covers AB minus this union. But, okay, and now we invoke compactness again. And I'm just going to be very explicit here. So this is a union of open intervals, but it's its complement. That's what set subtraction is. We'll have to do 2 pages here. Okay, so let's go 2 pages because that's where I put the other. So we're invoking compactness. So let x1 to x, we're going to do L because we used M as the upper bound. So there's a lot of indices here. So always pause the video if you need to slow down, make sure the indices are correct, such that the union over, L equals 1 to capital L of B delta sub X sub L of X sub L is a cover of N equals 1 to capital N of I sub N. Okay, so now let's call this guy V, this guy W. That means that W union V equals, let's call it capital Z, is the union over J equals 1 to N plus L of theta sub J, where theta sub j is I sub j for 1 less than or equal to j less than or equal to n, and theta n plus j is b delta sub x sub j of x sub j for n plus 1 less than or equal to j less than or equal to n plus l. So I'm going to lump them together. Z is an open cover of A, B. So now we can classify every point in our domain. So now we're ready to construct our partition based on Z. And so that is, take P equals, I'm going to call these Y's because I already called these X's and I gave them subindices. I guess I could have called these Y's since X is usually, but just to be careful here. And so I'm going to give this another index R, okay? And that's going to be a partition. So you can take it, you can partition it, you have some freedom of the interval, but such that the closed interval y sub r minus y sub r is contained in theta sub j for some j. Is wholly contained, so that I essentially can split. I'm going to define C1 to be the set of all R between 0 and R, 1 and R, such that y sub R is wholly contained in I j for 1 less than or equal to j less than or equal to, or for some j, and C2 to be the set of all R. So we've now constructed our partition, and so now we're ready. This is contained in let's just write it out. B sub delta sub x sum j for sum j. Okay, so now I'm going to claim that that's our partition. Now we're ready. Show the upper sum. I forgot a key point of the proof. I needed to specify. Oh, I needed to specify what S is. So I'm showing, you know, I have arbitrary S. I define AS like this, but I need to name S as a function of epsilon. So this is less than epsilon over 2 times B minus A. So this is going to be control on F. This is going to be epsilon over 2 times capital M minus lowercase m. That's why I needed to say m is strictly greater than lowercase m. And so this is control on size of discontinuities. So yeah, so sorry, I forgot that earlier. So we're talking about a specific S and a specific, I'm going to call this T. And epsilon was fixed at the very beginning. So now we're ready. So this is the upper sum minus the lower sum. And this is equal to the sum over J and C1 of the set oscillation of F on xj minus 1 to xj minus xj minus 1, and I'm going to do a different color here, minus the sum J in C2, set oscillation of F xj minus 1, xj minus 1. Okay, now this C1, right, we don't know. This is our set of basically where we have discontinuities because I sub j, this finite set, gave us control over the size of the set, but we have discontinuity here, possibly. So, with at least one point in there. So, this is less than or equal to worst case scenario, no control, times the measure of the union over J and C1 of closed interval and then plus we know that the difference between xj and xj minus 1 is no worse than b minus a. So this is pretty crude bound here. Set oscillation. Oh, no, it's in the complement. Sorry. You can't be that crude. Okay, so this is so the set oscillation, we have, these are in C2. Okay, so we know that the difference between xj and xj minus 1 and xj, sorry, I reused xj, so call these xj tilde, because I defined our partition. Oh, sorry, no, yeah. Y, these are the y's. Y, and Y. Then these guys, we had control over how far apart they were. So these were, we had a cover over the complement of our set of discontinuities, or set of discontinuities of order S, if you like. So this is less than S. So we know that set oscillation is less than S. So simply multiply by S times the measure of the union over J and C2 of YR minus 1 YR. Then let's make a new page here. So then it's just it's easy bounds from here. So this is less than or equal to m minus m times, okay, so these intervals are completely contained in the ij's. So this is the union, measure of the union of, we call these n's, over all the in's, and plus s times b minus a, right? The sum of the intervals is certainly no worse than b minus a. And this is less than or equal to m minus m times t plus s times b minus a. And we defined t to be epsilon over 2 m minus m plus s times epsilon over 2 b minus a. Epsilon over 2 plus epsilon over 2 is epsilon, and we have Riemann integrability. So yeah, it's a bit detailed. We have 5 main steps. Just as a quick overview, I've gone over 20 minutes, which I try not to do, but this is kind of a longer proof. So I'll go over the outline one more time. So you define this AS as in the lemma. So discontinuities of order S is basically what that is. Get an open cover of AS with open intervals because you know it's measure 0. Then invoke the compactness of AS through our lemma to get a cover, finite subcover of our set of discontinuities of order S. Then invoke compactness of its complement to get a finite subcover for intervals of all the intervals you get from continuity everywhere else, or continuity or discontinuity of order less than S. So you have control over the jumps. And then with that, you construct a partition of Z because now you've covered the whole set because you've taken its complement as well. And then do the technical calculations, make sure your epsilons and deltas are correct. That's all. Thank you guys for watching, and that should be it for Riemann-Lebesgue.